Have you ever watched an ice skater start a spin, and then suddenly they pull their arms in and start spinning like a top? It looks like magic, but it's not. It's this silent, invisible law that's running the show for everything that spins, from a kid's toy to a whole planet. Today, we're going to pull back the curtain on that law, angular momentum. So yeah, this is the classic puzzle. The skater's out there, arms wide, spinning kind of slow. They pull their arms in close and bam, they accelerate into a total blur. How in the world does that work? It's all physics, and by the time we're done here, you'll get it completely.
So here's our roadmap. We're going to start with the absolute basics of spin. Then I'll introduce you to what I call momentum's twin. From there, we'll actually define angular momentum, talk about torque, that's the push, and then we get to the big one, the law of conservation. That's the key that unlocks everything. And finally, we'll talk about why this is so much bigger than just an ice skater.
Okay, let's dive right in. Section 1, the physics of spin.
You know, that ice skater is really just the tip of the iceberg. The exact same invisible rule that makes her spin faster is what keeps planets locked in their orbits, and it's what helps a gymnast stick a perfect landing after a crazy flip. This is a fundamental force of nature we're talking about.
So to wrap our heads around this new idea, we're going to use a really powerful analogy. Let's meet momentum's rotational twin. Before we get into all the spinning and twisting, let's just back up to something we all intuitively understand, an object moving in a straight line. Trust me, if we start here, all the new stuff is going to feel way, way easier.
This slide lays it all out for us, side by side. So in straight line motion, you have mass, right? That's just an object's resistance to being moved. Well, in the spinning world, you have something called moment of inertia. It's the same idea. It's just resistance to being spun. A linear force is a simple push or a pull. Its rotational twin is torque, that's a twist. And finally, linear momentum, which is the quantity of motion, has its twin in angular momentum, the quantity of rotation. See? It's all connected.
Okay, with that parallel in our minds, let's get to the main topic, Section 3. So, what is angular momentum?
All right, here's the official physics definition. Angular momentum, we call it L, equals R cross P. Now I know, it looks like a scary equation, but don't let the letters fool you. It's actually pretty simple once you see what R, P, and that little X really stand for. So, let's break it down. That equation is really just three simple ideas mashed together. First, P is just the object's linear momentum, basically how much oomph it has. Then there's R, which is simply how far the object is from the center of the spin. And that X? That's something called a cross product, which is just a fancy way of saying that the angle between the object's motion and its distance from the center is absolutely crucial. Think about opening a door. You get the best result, the most spin, when you push on the edge, far from the hinges, and you push straight on, at a 90-degree angle. That's all this is.
Now, here's a kind of weird part. Angular momentum is a vector, which means it has a direction, but it's probably not the direction you're thinking of. If you have a wheel spinning flat like a record on a turntable, its angular momentum isn't pointing around in a circle, it's actually pointing straight up or straight down, right through the center.
And believe it or not, there's a super simple trick to figure this out. It's called the right-hand rule. Seriously, you can do it right now. Point the fingers of your right hand out from the center, that's R. Then, curl your fingers in the direction the object is moving, that's P, and wherever your thumb is pointing, that's the direction of the angular momentum, L. Simple as that.
Okay, so we know what angular momentum is, but what changes it? And that brings us right to Section 4, torque.
The connection to linear motion just keeps going. If you want to change an object's straight-line momentum, you have to apply an external force, right? You have to push it. Well, if you want to change its angular momentum, its spin, you need an external torque. You have to give it a twist. If there's no outside twist, the spin doesn't change, period.
And that one idea, no external torque means no change in spin, is the absolute key to everything. Welcome to the main event, Section 5, the law of conservation.
This right here is one of the most fundamental principles in all of physics, the law of conservation of angular momentum. It says that in any isolated system, one with no outside twists acting on it, the total amount of angular momentum, L, must stay the same. It can move around within the system, but the total never, ever changes. It can't be created, and it can't be destroyed. So let's bring it all the way back to our skater. If we ignore that tiny bit of friction from the ice, there are basically no external torques acting on her. She is her own little isolated system.
And this slide, this is the secret. This is the whole trick. Since her total angular momentum, L, has to stay constant, she can make a trade-off. When her arms are out, her mass is spread out wide. That gives her a large moment of inertia, which means her spin, her angular velocity, is slow. But the moment she pulls her arms in, she pulls all that mass toward the center. Her moment of inertia shrinks, becoming small. And because L has to stay the same, her speed has no choice but to increase to make up for it. She spins fast. It's not magic at all. It's just a beautiful exchange.
And this law doesn't just work on the ice rink. It works on a cosmic scale. Think about a meteor whipping past Earth. Gravity is pulling it, yeah, but it's pulling it straight towards Earth's center. That pull doesn't create any twist, so there's zero torque. That means the meteor's angular momentum is conserved. So as it gets closer to Earth, as its distance r gets smaller, its speed, v, has to increase to keep that angular momentum constant. It's the exact same principle as the skater, just with a planet and a rock.
And that brings us to our final section, where we can zoom out and see just how important this whole idea really is. Section 6. Why this law matters.
I love this quote from the physicist Dan Kleppner because it really says it all. This is an independent physical law. That means it's not just some neat little consequence of other rules. No, this is a bedrock, foundational pillar of how the universe is put together, right up there with the conservation of energy.
Seriously, we have never ever found an isolated system where this law has been broken. It's not a suggestion, it's not a guideline. It is a core rule of the cosmos, from the tiniest subatomic particle to the spin of the biggest galaxy.
So, I'll leave you with this question. Now that you know the secret, where else can you see it? Think about why a bicycle wheel is so stable when it's spinning, or why a helicopter needs that little rotor on its tail, or even why we only ever see one side of the moon. What other parts of your world are being silently and powerfully governed by this one incredible, unbreakable law?